All right, we're gonna get started in 2 minutes. Apologies for the little delay. Great to see everyone. All right. So, good morning. We are the community for Rigor. For those of you, okay, perfect. For those of you who are not familiar with us, we are an NIH, NINDS funded initiative to create an online curriculum to teach, learn, practice, and promote scientific rigor. So from A to Z, everything you're gonna need to know as a young grad student or as a professor who needs to teach this material to your students to do good science. So a lot of people throw the word rigor around, and we have found by talking to students and people at conferences through hundreds of interviews with grad students that many times they don't even know what that means. So we're here not only to create the online, free online curriculum, but also to bring together this community of people who do know what that is and who want to make science better together. So not only we're creating the free online curriculum, but we're also bringing together this global community. So this is the first time we go public with this conference. The past two versions were annual meetings for the C4R team. By the way, please NIH people raise your hands. Thank you. Shai, Mariah, Devon, thank you so much. Also, my colleagues from the center team. So raise your hand so everyone can see you. Okay, so you should have one person from the center team on each table. If that's not the case, I'll ask my colleagues to please spread across tables so you can represent. All right, perfect. Wi-Fi, C4R25 Conference, password Better Science, all lower caps. We have a very tight program today, so I'll try to be brief. Rigor's Raven, for those who don't know what that is not a penguin, I promise you. We picked the raven as our avatar because it's one of the smartest animals in the animal kingdom. It knows how to use tools, it knows how to communicate, it's fun, it's funny, it's a trickster, but it's also too confident. So it can, sometimes his tricks can bite him on his tail feathers. So that is our call to everyone to be very careful with the science they do. We know everyone has the best intentions. Everyone in here wants to do something good for the world. Oops. So yeah, that's our Rigorous Raven. If you wish to add your affiliation, the name of your organization, your company, your university, please do so to your badge. I mean, if you want to add it to your badges, there's markers on the table. You can go ahead and do that. If you want, you can add your pronouns if you feel comfortable with that. It's really up to you. There's going to be coffee available in the back of the ballroom. So if you look to the back, you see those big doors over there. There's going to be a coffee break, and you're welcome to go have coffee over there. Same for the lunch. So we're going to have lunch together up here. It's going to be also served. The buffet is going to be served in the back, at the back. Very short talks today. So we did this on purpose so that you can approach the speakers if you have burning questions, and that way we also promote more connections. So if you notice that the talk went too fast and there was no time for Q&A, it is on purpose. You please go ahead and keep those questions and ask them to the speakers afterwards. And with that, I'll give you our, who I call fearless leader and PI, Conrad Cording.
Wonderful. I'm not sure about the fearlessness. Thank you so much, Caro, for putting this together. I mostly want to thank all of you for being here. Rigor is more important now than ever. Science has trouble. Data sets are getting big. Big data sets allow us new ways of screwing up our science. And at some level, there have always been people in favor of rigorous approaches to science, probably since the times of the Greek. And they have always been playing an uphill battle against forces that want to make epistemology much easier, but just wrong. And so it is a supreme delight to be here. I want to just thank a couple of groups that are here. I'm super thankful for NINDS for actually taking Rigor seriously. the celebration of nature papers that are like shallow and misleading needs to go away, and I'm really thankful for them taking a leadership role. I'm thankful to all the meters that produce great materials and really think hard about what's missing on the science of in science. I'm thankful for all our advisors that are here. I'm thankful for all the non-team members that are here working towards making science more rigorous. And most importantly, maybe, I'm super thankful for the C4R team who's here, who are working with me on producing wonderful materials. Now, without going for too long, I want to do something different. I want you all to take 1 minute now to take someone else on your table and tell them an idea you have about rigorous science. Go. Sort of as a hello. Oh, okay, everyone. Hey. I'm sorry, I need to get you back. But I think this is what I wanted to do with this is just the fight against bad science, against non-rigorous science, is not one that any one of us can win. It was great seeing you talk with one another. It was great seeing the engagement that you have there. Briefly, where we stand as C4R, we are now finally at that situation where we have a couple of products that I think we're very happy about, and it's a new era for us as a group, and it's wonderful that you're all here with us. And it is 9:15, which means we have to move to the next meeting. Thank you all for being here. Thank you for what you do for rigorous science.
All right, that's good timing. Thank you. I forgot to mention another very important group, two groups, meters. So these are our collaborators. This curriculum is being made by professors from all over the country who also got grants from the NIH and INDS. I want those people to please raise your hand so everyone can see who you are. Ask questions, mingle, connect with them. They're called meters, but in our internal language, but they really are called collabs, so collaborators. And also our advisors. There's a few advisors in the room. Jason Tilak is also here. So if you want, also please approach them and connect. And with that, I'll call my colleague Hao Ye, curriculum development lead, to run our first workshop of the day, randomization.
Yeah, is it possible to have the laptop here? Yours. Mine? Okay. How's that gonna work?
Okay. 1 second.
1 second, sorry.
Can we have your
All right. Yeah, thank you for being patient while we figure out our teamwork. We definitely rely on a group of people to help us out with improving rigor. All right. Thank you all for being here. My job right now is to introduce kind of our product and what we're doing for this session. At Community for Rigor, we are creating free online educational materials to provide instruction and training for rigor. Some of these materials are designed to be used directly by researchers or students through self-guided learning. Some of these materials are intended to be used by instructors in classrooms. What you are going to see here is a particular shortened version of a unit that we call our meeting version. Its goal is to facilitate small group discussions, such as in a lab group that could be led by, like a postdoc or an upper-level student. We're going to go through this slide deck. It should take about an hour. We're going to try and get it a little bit shorter because I know we're running a little bit behind on time. It is an interactive session, so we do welcome your participation. This isn't a Zoom, so you can't just sign off when we start the breakouts. We are going to ask you to bring out your laptops and play along with us. We have feedback. We have a feedback session at the end of this hour. So we ask that if you have feedback about, constructive feedback about what the materials are, what they are missing, please hold that to afterwards. But for now, act as though you're in a classroom setting or in a small group setting. If you have questions about that require clarification of the content, we welcome those. So thank you. All right, thanks, Zach. Okay. This lab meeting unit is on the topic of randomization. I want to thank our original draft authors, Mary Harrington and Lisa Mangiamelli from Smith College, as well as April Clyburn-Sharon, who led the initial development of this unit, along with the rest of the center team, who have provided feedback, revisions, software development, very importantly, and user testing and integrating that feedback into this slide deck. Thank you. I can see if I can click. Okay. All right. So, okay. Lesson 1 is knowing results are real. Why do we care about randomization? Let's look at an example study. So let's suppose we are interested in testing a lithium treatment for ALS. Our hypothesis is that lithium treatment is going to improve survival in an ALS mouse model. Before the study, we're going to measure things like age, sex, weight, and time on a rotorod. And then as part of the outcome measures for the study, we're going to look at survival time after treatment. So we have our wild-type mice. We have our lithium carbonate solution, which is our treatment that are going to be given to some of the mice. And then we have our saline control that is going to be given to the mice that are in the control group. So the first thing we're going to do is assign mice to treatment groups. This is how the procedure is going to work. For every cage that has 4 mice, we're going to first catch 2 of the mice, give them the saline control, and then the remaining 2 mice are going to receive the lithium treatment. Initial findings are very promising. So this graph here showing all of our data points. You can see the scatter plot here of the survival time in days for the control group on the left, for the treatment group of mice that receive lithium on the right. We see it looks like a pretty strong effect here of median survival increasing for the mice that receive the lithium treatment. So the mice that are treated with lithium have longer survival. But suppose our reviewer asks, what if the change in survival time is actually due to some other kind of systemic difference between the groups, other than whether the mice received the lithium treatment or the saline control? So what we're going to do now is we're going to examine several variables that are measured during the study. This is part of our interactive learning experience. We're going to ask you to explore these factors and see if one of those might have influenced the results. So I know we have a website set up with links for these activities we would like you to navigate to. That website is C4R.io /demo, DEMO. That's C4R.io/demo.
Anyone have any trouble navigating to the website? And we're supposed to click on lesson 1, knowing results are real join activity. Is that right?
Yes, that's right. Zach is going to show you the navigation to that website as we speak. The first activity here, knowing results are real, there is a purple button for join activity. All right. How many people are still waiting to connect to the Wi-Fi or getting to that page? All right, so we'll wait a little bit longer. It is C4R.io/demo. In terms of this activity, we are interested if you see a statistical association between the two variables. And in the interest of not overburdening our software developers with all of the text revisions, we have not included all of that description in the activity. Okay, so let me walk you through kind of the first screen. So you will see a screen that shows you, again, that scatter plot of survival time between the two groups. And there will be a button for you to get variables. So you're going to be assigned a variable to explore as part of the examination of potential covariates that have influenced the results. So Zach here got sex as a biological variable. We can click continue. The first thing we're going to look for is there a systemic difference in this variable between our treatment groups, right? So we have our control group, we have our treatment group. Is there a systemic difference in this specific variable between these two groups? We can answer, do you see a difference? You're not sure, or you don't see a difference. So you can make a selection and continue on to the next page. And then the second part of the activity is going to look for, is that covariate also somehow statistically associated with the outcome variable? Is it associated with survival in days, right? So now we're looking at whether sex as a variable is driving any of the differences between survival time. So again, you can select, I see a relationship, I am not sure, or I don't see a relationship. Make your selection and click continue. And then on this final screen, you'll be able to see kind of the collected results from this group here in the room. So 5 possible variables could have been assigned to any one of you. These are sex, weight, time to fall, litter, and age. The most common answer for whether someone observed a relationship between that variable and the treatment condition is given by the box at the top here, the most common answer. And then the most common answer for whether someone observed a relationship between that variable and the survival in days is shown in the second box here. And then what we're looking for here is really like, is there some kind of covariate or confounder that is influencing the results, right? Is there a difference in that variable between the treatment conditions? Does that variable influence the survivalship and the difference in survivalship between the two treatment conditions? So we can go through and kind of look at some of these different variables. But the idea of this activity is to spur some discussion about looking for potential covariates and confounders for interpreting our initial findings. All right, thanks, Zach. Can we go back to the slide deck? Okay, So we're looking for if there's a systemic difference between the treatment and control groups for any of the variables. I'm sure some of you found some of the covariates did look like they had a substantial difference between the mice that were in the treatment group and the mice in the control group. But we're going to go ahead and focus on one variable in particular, which is time to fall. This is a measurement for the length of time before a mice falls off the rotorod in the context of this study. Time to fall is actually a proxy for disease stage. As mice have more advanced disease stage, they cannot hold on as long to the rotorod. So this measurement of time to fall is a proxy for how far the disease has advanced for that individual mouse. We can see here that if in the control group, the mice have a lower time to fall, so they cannot hold on as longer, suggesting they have a more advanced disease than the mice that are in the lithium treatment group. We can also see when we look at the correlation between time to fall and survivalship in days, there is a strong statistical association. So it's possible that this variable is also driving the results that we see where there is a difference between the control group and the treatment group in survivorship. So although we initially thought the differences between these two groups were due to the lithium treatment, right, the treatment instead of the control, they actually might be due to differences in the time to fall. And if we go back and think a little bit more deeply about our experimental design, we can start to figure out why that might have happened. Right? So why is there a systemic difference between the two groups? So if we go back to our assignment procedures, when we assigned the mice to groups, what we did is we caught mice and then we assigned them to the control group. So the mice that we caught first in each cage, the first 2 mice were assigned to the control group. Right, so, and then the remaining 2 mice received the lithium treatment. So what we actually might have introduced as a result of this assignment procedure is that the mice that were caught first were always the ones that were given the control. So if the mice that were easier to catch in this assignment procedure had some kind of difference between the other mice in the cage, that might introduce this systemic difference between the two groups. So our goal in this study, right, we wanted to see what the effect was of the treatment condition on survival, but what we actually ended up doing as part of the design of the study is we found that there is this variable disease stage with a proxy measure of time to fall that affected both the assignment of the treatment condition as well as the survivalship of the mice. So this is a confounder. Confounders are variables that disrupt experiments. A quick definition is that a confounder is a variable that influences both the independent variable and the dependent variable in a study. And when we have confounders in our study, they can mask or amplify the influence of the independent variable that we actually are trying to study the influence of. So what we needed to do is actually perform a random assignment of mice to the control and treatment groups. Randomization is a way that we do that. It enables an accurate assessment then of the effect of lithium treatment. And proper randomization is going to help us to eliminate differences other than whether the mice received lithium or saline treatment. So again, this is the scatter plot of the initial set of results with the non-randomized group assignment, where we saw a difference between control and lithium groups in their survivorship. And then when we do proper randomized group assignment in this hypothetical simulation, we see that actually that effect, that difference goes away. So proper random assignment, here's how we need to do it. We're going to start by labeling all the mice used in the experiment. We're going to generate a randomized sequence. We assign the mice to the treatments based on that random sequence that has been generated. And then we implement the assignments and conduct the rest of the study. So next, we're going to learn a little bit about generating those random allocation sequences. So that is the end of our first lesson of 3 for this session. I see a question in the back. I think for that screen, there are the 5 buttons or 5 variables at the top. I think you should be able to click on those variables directly. Yeah. Thanks. Great question. Okay. Thanks. Next lesson. So, in lesson 1, we learned that improper group assignment led to an erroneous conclusion about lithium treatment. And using a random allocation sequence is a way that we can help with this problem. What makes an allocation sequence random? So in this activity, we're going to ask you to examine 3 different sequences that have been reported as randomized allocation, ask you to evaluate which one is truly random. So again, if you're on your laptop devices, go ahead and navigate back to that C4R.io/demo page and click on the Join Activity button under Lesson 2, Proper Allocation of Treatments. All right, waiting for people to join in. And in this activity, you will see 3 sequences of allocation sequence to groups A or group B. You will see some summary statistics below those sequences of the proportions of A and B in that sequence. If you like, you can also click the button Regenerate New Sequences to see what those generation algorithms are going to do. So you can play around with that, make some observations, and as well as look at the history of those proportions in the table below. And then if you scroll all the way to the bottom, you have some questions for you. So first, you're going to select which sequence you think is the random one, sequence 1, sequence 2, or sequence 3. And then write some explanation for why you think your selected sequence is the truly random one. So Zach is going to demonstrate a little bit. Zach selected sequence 1 with the reasoning that I like that it is even. Thanks, Zach. Okay. Question? Yes, sorry, that is the maximum run size. Thanks for that clarification question. All right, so here we see the results of the people in this room. I think if we continue to refresh, we can also get updated graphs here of the number of people who selected sequence 1, sequence 2, and sequence 3. And then if we scroll further down, we can see a little bit of the reasonings that have been provided. So we see things like the runs are surprisingly short, but frequency similar and no immediate pattern for sequence 2. Sequence 3, we have some responses like does not look ordered or changes the most when generating new sequences. I think is an interesting assessment. Can I ask who if you're comfortable sharing why whoever wrote that, why you wrote that, and what you mean by it?
Which one?
Changes the most when generating new sequences. That was you, Devin. Okay.
Well, if you hit generate sequences multiple times, you can see when you hit generate sequence multiple times, you can see that 1 doesn't really change at all, 2 changes but not that much, 3 goes unequal balanced back to different groups, so it doesn't seem tied to a particular underlying algorithm.
Okay. I think that is a very unique insight that like when we are doing random assignment and we're generating random allocation sequences, they should feel like there's no connection to the sequences that we have previously generated, right? Like if they're truly random, they should be independent of everything else that we have already generated. So that's actually a really, really great insight and thing to observe. Good job, Devin. Zach, can we go back to the slides? We'll actually get into it in the discussion coming up.
Real quick.
Yeah. Oh, I didn't even know there was a reveal. Okay, you did select the correct one. So sequence 3 was the randomized allocation. Sequence 1 was always alternating between A and B. And sequence 2 is our simulation of a manual allocation by a human who's trying to avoid certain patterns in the assignments. Okay, so let's go through kind of some of the issues with some of these sequences, especially the ones that we know are not actually truly random. So sequence 1 is this perfectly alternating sequence. It always alternates between assignment of samples to treatment groups, and it has some issues with it. So first is the potential for selection bias. If the experimenter knows that the next treatment assignment is going to be treatment or control, they might unconsciously or pick a preferred mouse to be in a specific group because they know what that next group assignment is going to be. Another problem that can happen is order effects. So subjects or samples could be ordered in some way, such as by size or by batches. And if we always have an alternating sequence, that can generate a small but consistent difference between those two groups. So as an example, if we have mice that are just happen to be ordered by size, like so, and if we always have a perfectly alternating sequence between group A and group B, even though these differences are small, there's always a consistent difference that the mice in group B on average are larger than the mice in group A. And so that can generate a systemic difference between these two treatment groups. Sequence 2 is a sequence that simulates human randomness. It mimics a sequence that is generated by a human who is trying to balance the number of individuals in the two groups. So what happens is humans can perceive that there are too many A's or B's in a row, so the maximum run size. They might perceive that to be unnatural and then try to limit the run size to 3 or less. And this can also lead to selection bias. So someone might think, well, we've had several sicker-looking animals in group B, so I'll put the next healthy-looking one there to balance things out. And so this form of like unconscious selection bias can again affect kind of like the systemic differences between the groups and bias the results. Sequence 3 is the true random sequence. It is a randomly generated sequence where each element has an equal and random chance of being A or B. This unpredictability in the individual assignment values in that sequence is key. It also addresses these particular issues. It addresses selection bias because an experimenter cannot unconsciously select a preferred sample for a particular treatment group because each treatment is assigned at random. The next assignment is random to and unknown to the experimenter. It also is a way to address order effects. So with a truly random allocation sequence, the order of samples should not matter because each sample's chance of being assigned to either the treatment group or the control group is going to be independent of all the past assignments. So that kind of like independence criterion that Devin picked up on in observing the allocation sequences. So the key discerning feature here of a random sequence, it is unpredictable. And because each sample has an equal and random chance of being assigned to treatment or control, the effects of covariates or confounders, even ones that are unknown to us as experimenters, can end up being balanced across groups. Because a truly random allocation sequence is unpredictable, it can also have these other features that may be a little bit unsettling. So it can have long runs of the same value. So for example, 7 assignments to group A in a row. It can generate unequal group sizes because the generation of the allocation sequence is not trying to enforce balance between the sizes of the two groups. Also might not feel random because of those long runs. And so now that you know about how randomization can address biases, let's look at some of the common methods of allocation that might show up in the literature. So some common methods for treatment assignment, just kind of like hypothetical experiments. So maybe, we'll see things like someone will inject a mouse with a treatment, and the next one with a placebo, and then repeat. So doing that alternating treatment assignment. We might haphazardly assign mice to groups, making sure to balance things out. Or assign individuals to treatment or control based on things like the date of birth or the date of trial entry in participating in the experiment. So these are all examples of kind of things that might happen in experiments and are things that we generally want to avoid because they aren't true random assignment in experimentation. So for now, I want to ask you to discuss a little bit with someone next to you or at your table, kind of what are the sorts of biases that can arise from some of these methods of assignment? What are some of those issues that might come up? Go ahead and spend some time discussing with each other, and then I might call on some of you to share some of your thoughts. Yeah, can we go back? Okay. Hey, hello. I would like to call the class back to session. Hello. Hi. Oh, thank you. Okay. Hi, everyone. Okay. Let's start with the back of the room. Anyone have any insights to share about issues arising from any one of these assignment methods?
truly random. And well, the last one I couldn't read properly because I'm sitting very far away. So I'll let someone else speak on that.
Okay, thank you. So I heard as a problem with the first method here is, again, that is a kind of alternating sequence and has some of the issues that were previously discussed. And the second way of assignment of haphazardly assigning mice to groups also introduces that human potential for human error, human bias to affect the assignments. Do we have someone with some thoughts about the third method of assignment here and issues arising from that?
I don't necessarily have something exactly about the third, but are you leading us towards the fact that we've not accounted for the other variables like we did, or confounding variables that might influence the randomization when we go about the practice of randomization using these things? So I guess my answer is the biases would be that we haven't accounted for the multiple other variables that might ultimately end up influencing explain it better, Sarah. The multiple other variables that might ultimately end up influencing our results when I don't know how to correct it. Maybe I should stop talking. But I feel like there's something here where when we just practice these practices, we are not taking into account that there could be confounders that influence these practices.
That wasn't the intent, but I'm glad you mentioned it, and it does actually foreshadow what's coming up in lesson 3, which is with issues that are things like date of birth or date of trial entry. Those are potential covariates that could influence the results. So if we do want to account for those, we will need some kind of randomization or assignment method that does properly do that while still maintaining kind of the properties of randomness that we want. Mickey?
One thing I brought up is that it depends on the sample size. With small sample size, like some people do 8 mice per group, you can't haphazardly do stuff because it's too small for a haphazard. Too small for haphazard, or even a random number generator with a very small sample size won't be random enough. Yeah.
Great, thank you. That was a comment about sample size, that even so with certain experiments with small sample size, you can't do haphazard assignments, and there are lots of kind of issues with small sample size that will also need to be accounted for. That's what I'm hearing.
Is this on?
Yeah.
But also, any method you use for randomization, you want to not use a procedure that could be predictable in some way to avoid any kind of unconscious bias. So that's what I see in that third one there.
Yeah, thank you. Alex is pointing out we had multiple slides mentioning the unpredictability is kind of like the key to the random assignment, and that unpredictability is not really present in any of these methods.
I'm wondering how you still maintain roughly equal treatment and control groups using these methods.
Yeah, so I think for these methods, if the desire is for balance between group sizes, some of these methods may be ways of trying to get at that balance, but then create issues due to lack of randomization. And there are methods that there are randomization methods that do introduce balance, and those are some of the things we'll be getting into in lesson 3. So thank you.
You asked about the third one there, and I think one of the issues could be that if you assign based on date of birth, there could be seasonal differences in the way that rats are reared. It could also be that the company that provides the rats might switch from one provider to another in between, and suddenly half of your rats are from one group versus in the other condition they're from another one.
Yeah, thanks. That there are some definitely batch effects that could happen with assignment based on date of birth or date of trial entry. Okay, Wrapping up with this lesson, remember the goal of randomization, all right, we're trying to eliminate systemic differences and enable valid interpretation of research results. So that's kind of like the aim that we're going for with introducing randomization to support research rigor. Okay. One of the key things I think Alex actually mentioned is the unpredictability. So some things that are important to keep in mind when applying an allocation sequence, you want to first select the individual sample or participant or animal that you are doing the assignment for, and then look at the allocation sequence to determine what that assignment is. If you know what the assignment is when you select the sample, that can, again, introduce that selection bias because you now know what the assignment is before selecting the individual that is being assigned to a particular treatment group. Okay, so next we're going to explore some different methods of randomization that can address issues like imbalance and known covariates. So lesson 3, the last lesson of this meeting version of the unit, is choosing a randomization method. Proper randomization method or proper randomization helps eliminate systemic biases so that we can accurately measure treatment effects. What are some of the sources of these systemic biases? We can have things like researcher biases. For example, experimenters who are manually adjusting groups or selecting samples. We might have covariates, like sample characteristics such as age or sex that could affect results. We can also have environmental effects, things like time of day, temperature, or light, that can influence groups differently. So randomization methods can address these different sources, and in this lesson, we're going to look briefly at 3 different approaches. We're going to look at simple randomization, we're going to look at block randomization, and we're going to look at stratified randomization. So the setup for this lesson is a slightly different experiment. We are now looking at dopamine modulation of song learning in zebra finches. Some of the measurements we're going to look at beforehand for these animals are things like their singing quality and song learning ability. We have a study environment that includes a lab that might be near a noisy hallway with light and temperature differences throughout the room. And our outcome measures the resulting song learning for 60 days for these 30 zebra finches that come from 5 different clutches, 5 different families, different lineages of the birds. Again, we have the dopamine. We have 2 treatment conditions. We have the dopamine, which is the treatment that we're observing, or trying to determine the effects of, and our saline control. Okay. First method is simple randomization. We have already introduced this in the previous lesson. It is the most basic technique, and it works by assigning samples to treatment groups using this random allocation sequence, where each sample has an independent and equal probability of being assigned to group A or group B. When we do simple randomization, we perform this set of steps where we assign these birds a unique ID number, generate the random allocation sequence, select the bird, and check the allocation sequence to perform the assignment to group A or group B, and then we have our resulting allocations of these birds. We might notice that with this sample size that there's an imbalance between groups. So while the birds have been randomly assigned, the groups are not the same size. And this is an issue that can be very apparent when we have small sample sizes. So with small sample sizes, so for example, 30 or fewer samples, imbalance in group sizes can reduce the effectiveness of statistical analyses. A more relevant imbalance might be is that if there is a factor that is unevenly distributed between groups, so some kind of additional variable that causes a systemic difference between groups A and group B. So for example, what if the treatment groups are exposed to different environments? So for the sake of our experimentation, we might have our birds assigned to in treatment group A in a particular rack, and the birds in group B assigned to a different rack. What if rack A is by a noisy hallway and rack B is in a cold, dark part of the lab? There might be these environmental differences between where the birds are housed that then causes a difference. It causes a difference in the outcomes in addition to the effects of doing treatment A or treatment B. So that's where we might look into a method like block randomization. So block randomization is a method that can help us to enforce balance. It divides the total pool of samples into many experiments called blocks, and then within each blocks, we can use a method like random permutation to make sure that samples are evenly assigned to the different treatment groups. So what we might want to do then is to choose blocks that will map onto environment conditions, such as time or environment, and that way we can ensure that whatever environmental variations there are within those different environmental variations, there's still balance between treatment groups. So what that would look like in this case, we want to determine the block size. So the block size has to be a multiple of the number of treatment groups. And ideally, that you want the block size to line up with the natural experimental subdivisions that you seek to balance. So in our case, with the zebra finches and the racks, we can think of each rack as an individual sub-experiment that we then that help us determine our block size. So if we have 2 treatment groups and racks that can fit a maximum of 10 birds, let's use a particular block size of 10 with 3 blocks so that we have 30 total birds assigned to these racks. And then what we'll do is perform a random permutation to balance the treatment assignments within each block. So within these 3 blocks, we can balance the assignments to group A and group B, repeating that for all the blocks in the study. And now, regardless of where we place our racks within the lab, there's always an equal number of birds assigned to group A or group B within each rack. So even if the racks are exposed to different environmental conditions, we still have balance between the groups. So block randomization is a way that we can balance environmental properties, but what about things like sample characteristics? What about things like age and sex? So that is where we might turn to a method like stratified randomization. Stratified randomization ensures balance between treatment groups of specific sample characteristics that might influence the study outcome, and then we can divide the population into subgroups based on those chosen covariates. So the first thing that we will do for stratified randomization is determine the number of strata. So we might choose some important covariates that we think are going to be influential and use those to determine the strata for our experiment. For this example with birds that have different clutch lineages, we have 5 clutches, so we can go ahead and see what it looks like to have 5 strata for this study. So again, we'll use a random permutation to balance treatments within each strata, so ensuring that there's an equal number of birds assigned to group A and group B within each clutch. We repeat that for all our clutches, and now we have an equal number of birds assigned to group A or group B, regardless of what family they're in. And so this is a way of ensuring balance across the groups with respect to this particular covariate. So let's review again some of the pros and cons of these 3 different methods. So with simple randomization, the setup is relatively easy, but we have this issue that group sizes can be imbalanced, and also that we're not accounting for environmental effects or sample characteristics. With block randomization, that's a method we can use to try and balance treatments across time and space, but it's also a more complex method than simple randomization. And then with stratified randomization, it allows us to balance treatments across covariates, which can be really powerful because we know that some of these covariates or confounding variables can have an influence on the outcome. Some of the trickiness with stratified randomization is that we have to be able to measure the covariates in advance of doing the random assignment. So if we're doing any kind of study where we're continuously enrolling samples or participants, we can't use stratified randomization simply because we don't know what those covariate values are going to be in order to perform the balance properly. Additionally, with stratified randomization, recommendations are that you need 10 to 20 samples per strata to make sure that you have enough statistical power for your analyses. So in deciding a particular randomization approach, we want to consider these aspects like sample size, what is your existing population, what resources do you have in your lab to perform the experiment. We want to think about things like covariates. Are any of these sample characteristics potentially influential for the effect that you are trying to measure? We want to know if there are environmental effects that might influence the outcome of the study. We might also consider things like method complexity. What are our resources with respect to researchers, training, and implementation time for our experimental hypothesis? So I don't think with the time that we have available, we're going to go into this last activity, but we have created a little interactive flowchart that you can use to help guide your thinking processes on selecting among these randomization methods. So you can go through and click about kind of like things like what are these concerns that you might have of particular environmental variables or covariates, sample size, and things to choose from, and then that will generate a recommendation for you. All right. Whoops, sorry. So again, randomization, to wrap up, randomization is a way to help support rigor in your study. Different methods are available depending on like kind of which biases are important, right? Those are going to differ from case to case depending on your field, depending on what you are investigating, the issues that you are looking into, as well as your study constraints. In the full unit, we will have more on the implementation details of some of these methods as well as other considerations. So for those of you who are kind of internal to this project, look forward to that exploration in depth tomorrow, which will be led by Zach. But otherwise, thank you for your time and your participation. We'll take a little quick break before we switch over to kind of getting your feedback and your thoughts in a structured way. So thank you.
All right, please go ahead and take, say, about 5 minutes. Please stretch your legs. I'll call you all back in a little bit, and we'll move to collecting your feedback and your thoughts. Thank you for your time.